So I'm going to handle alkanes today. Organic chemistry, and within our alkanes, or by the end of this chapter, you should be able to name any alkane. Any alkane. Then you should be able to explain the physical properties of alkanes. Physical properties of alkanes. Then you should be able to discuss the synthetic pathways for alkanes and conditions for their formation. So it's like you have to be able to, be capable, or you have to gain understanding in synthesis. And so after that, you have to be capable of discussing the chemical reactions of alkanes. So gain understanding in the chemical reactions. So sometimes synthesis is called lab prep or lab preparation. Then chemical reactions, then mechanisms. Mechanisms for the reactions. So those are the things I'm going to focus on. But I'm going to first speak out. I've realized that if we follow our normal pace in school, it's not going to help. That's not how we study A level. Then the other thing, if we follow our normal timetable, that online timetable, well, it's also going to move a bit slowly. So I'm going to do the donkey work for you people. I'm going to weight lift, at least as you people are sleeping. I'm going to be recording these lessons. Then you'll access them at your free time. But remember, you don't have any free time. Just fix time. Get these recordings, put them on times 2. I've realized that when you put this video on times 2 speed, you're going to cover much in less time. So it will look like you're cheating the system by making your work simple. But as of now, that's what we're going to do. I'm going to be covering some parts with you as I record the other parts. You will find them. So let us move on with our alkanes. So from what we know, any alkanes are saturated organic compounds. Is what we know first of all, and you have to realize that under our alkanes, What we need to know is one, the general formula, general formula, which is CnH2n plus 2. That is it. So maybe when you're told to define, you will define the alkane as saturated. We know very well that its alkanes are lacking double bonds or triple bonds. So you will maybe say it's a saturated organic compound that consists of entirely single bonded carbon atoms. Organic compound consisting of entirely single bonded carbon and hydrogen atoms. So that is it. We've seen the formula. Now, under some of the examples of alkanes we are having, let me say, the name here and the formula. So the first alkane is methane. And it is written as H4. Then the second is ethane. Written as CH3 CH3. Or you can write it as C2H6. Why? Because the hydrogens are 6 and the carbon atoms are 2. And from this example here, you can see that my N is equal to 2 from the general formula. This one, from the general formula, my N is 2. And when our N is 2, when you multiply 2 times 2 plus 2 gives you 6. It's the 6 you're seeing there. So we move on to the next part. Then the other alkane is propane. The other alkane is propane. Then we have butane, pentane, and hexane. So this is CH3H2 CH3. For propane, butane has 4 carbon atoms, so CH3, CH2, CH2, CH3. Then pentane has 5 CH3, CH2, 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 CH1, 2, 3, 4, and 5. CH3. Hexane has 6. So CH3, CH2, 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 1, 2, 1, 2, 3, 4, 5, CH3, like that. So there are more. Pentane, hexane, etc. So when we move on to, there are some alkanes that are branching. Some branching alkanes do exist. So what are we going to do? And how do we name them? So branching, alkanes. We have an example, can be CH3, CH2, CH3, no, CH2, CH3, and at that point I'm having CH. At that point I'm having CH3. How do I name this? This is how we're going to name it. We are going to follow the IUPAC rules. So I'm going to follow the IUPAC rules. Now, in these rules, it's stated that the longest chain becomes our parent chain, and it's we have to look for a name to give this the longest chain. So this is our longest chain. These are the things you have to first identify. So the longest chain is that, and when you count the number of carbon atoms, 1, 2. So this is carbon atom 1, 2, 3, 4, and 5. So that one is an alkane with 5 carbon atoms becomes our pentane. So we've identified pentane there. Then the branching chain is having only one carbon atom. This is now our branch, and the branch has only one carbon atom. So we can, you may think of calling it methane, but we shall not call it methane. So what are we going to do? And by the way, when you so this our branching carbon atom, I was saying that it has one carbon atom. So when I try to generate the name for this, it's going to be I'm going to count the number of carbon atoms I want to position this chain. I want to position that chain. So I'm going to say it's 1, it's going to be 2 methyl 2 methyl pentane, 2 methyl pentane, like that. Why am I calling 2 methyl pentane? It's because our branching carbon atom, we would call it methane, but it's not methane. It's just deriving its name from methane. From this methane, I'm going to extract out to this part, and I call it methyl. So I will call that methyl. So it's like this one is an alkyl group. It's an alkyl group attached to our parent chain. So the methyl, first you recognize its position, recognize the position of what? Of that group that is branching from the parent chain. So it's going to be position and the group branching group, then the parent chain. Now you may wonder, why didn't I call it maybe 4-methyl pentane? It's because from our IUPAC rules, as you're reading this work, use Demystifying Organic Chemistry, that book made by Jobs Kaira. That I recommend you to use that book. So it's the book I'm using, and from the IUPAC rules, we have to we have to position that alkyl group in a position where it has the least number or the least position, the lowest position. So I have two ways of naming this: 1, 2, 3, 4, 5. Then the other student may start counting from this side: 1, 2, 3, 4, and 5, like that. So the student that counts from this side is going to give this group the lowest position too. And the student that counts from this side is going to give it 4 methyl pentane. So student A is giving it that, student B gives it that. Student A is correct. Why? IUPAC rules. You research about those rules and you'll find out more about them. Then when we move forward, you've seen how we name branching alkanes. Now if I'm having this, what do we do? Maybe CH3, CH, we have a branch there, this CH2, CH3, then CH2, CH2, CH1, 2, 3, 4, 5, to CH3. So automatically this one becomes my parent chain. Now this is the branch. I'm going to try to give them numbers, the carbon atoms in the parent chain, and try to give them numbers or allocate position while making this side chain having the lowest carbon atom possible. But there is one thing you shouldn't forget. There is one thing you shouldn't forget. These alkanes, first identify the longest chain. When you're identifying the longest chain, you're going to find out that from our chain, this one is a possibility of being the longest, and the other student may say no, this is the longest chain, that one, and this is the branch. So you have to arrange the compound very well. Arrange it and see, find out which one is the longest chain. But so one can, when you choose the longest chain, you will find out that this chain can be stretched such that this part, I write it there, followed by that CH2, followed by this carbon atom CH. Then I make this one a side branch. I seeing that, then I move on to, so it's like I'm counting 1, 2, 3, 4, 5, 6, and 7 there. So it's going to be, this is 1, 2, 3. Then the fourth is this CH2. Then fifth. Then CH2, 6, CH3, which is the 7th. Are you seeing that now that one becomes our side branch? So how many carbon atoms are we having in the longer chain? 7. So we have 7 carbon atoms, and we shall call the parent chain, we shall name it heptane. We know very well that that initial there, hep, means 7. So, and the side branch is going to be our methyl. It would be methane if it is CH4, but since it's CH3, it's methyl. So which position is it having? It's having the 3rd position. So we name it 3-methyl heptane. Like that. So I'm going to move on to physical properties. I'm going to move to physical properties. And under physical properties, let's say physical properties. And under our physical properties, we have boiling point, we shall look at melting point, so when you look at these two, the boiling and melting points of alkanes increases with increase in number of carbon atoms. So this one increases with increase in number of carbon atoms, like that. So, and since the number of carbon atoms is increasing, relative molecular mass also increases. So melting point and boiling point are going to be depending on the increase in relative molecular mass, so the increase in carbon, the number of carbon atoms, and this is due to increase in van der Waals forces of attraction between the molecules. So this is due to increase in increase in van der Waals forces of attraction between the molecules. So that one is our boiling point and melting point. Then the other thing we shall look into is that we shall group our alkanes into some divisions. I'm going to call it we have alkanes with 1 to 4 carbon atoms. So alkanes with 1 to 4 carbon atoms. These ones are they are colorless gases. Then at room temperature, then alkanes with 5 to 17 carbon atoms are liquids with 5 to 17 carbon atoms. These ones are liquids. Then the other thing, the remaining higher hydrocarbons are all solids. So alkanes with carbon atoms greater than 17, these ones are solids. They are solids like that. So you can try to at least pattern this understanding with the boiling point. We said that that boiling point is increasing with number of carbon atoms, and since alkanes with carbon atoms greater than 17 are solids, what do you expect? Solids are having a higher melting point or boiling point compared to liquids. So you can at least pattern that with boiling, melting, number of carbon atoms, van der Waals forces of attraction, and the other property we have to look into, the other point is all alkanes are insoluble and immiscible with water. So all alkanes are immiscible with water. So they're insoluble, but they are soluble in organic solvents like trimethyl, trichloromethane. So, but are soluble in organic solvents like trichloromethane, trichloromethane, written as that. So that is it. Then when we move on to the next, the density of alkanes increases with increase in molecular mass. So density density increases with increase in molecular mass. So these are the physical properties. I'm going to talk about the other things you have to read them. The other things you have to read them. So they may give you graphs to plot a graph of boiling point against the molecular mass of alkanes. Then from your graph, determine the boiling point of octane. Explain the trend in boiling point. So you have to at least fix in that knowledge. Then we'll move on to chemical lab preparation. Lab prep. This one, that's my major point of concern for today. Lab preparation. It's where most of the questions are coming in. All this stuff is just to give us understanding of what we are going to deal with, but most of the questions are generated from lab preparation and reactions. It's where the chemistry is. So other lab preparations or synthesis, stroke synthesis. We have our first preparation is catalytic hydrogenation of unsaturated hydrocarbons. So this is hydrogenation. I would summarize it as that. Hydrogenation of unsaturated hydrocarbons. So what are these unsaturated hydrocarbons? We shall cover them. Alkynes and alkenes. These are the unsaturated hydrocarbons we are having. So the first reaction is going to be this is the basic reaction. CnH2n and by the way, take note, the formula here is that one is the general formula for any alkene. That one is the general formula for any alkene, you know. So from that, I'm having hydrogen. Since it's hydrogenation, we are adding hydrogen and using a catalyst, nickel and 150 degrees Celsius. So there are other alternatives people use, but I don't like alternatives at a younger age. we are still on baby steps, so it's better we have only one root. First master nickel. So from an alkane, it will give us the general formula for from alkene to alkane, like that. Then we talked of alkynes, these ones. We talked of alkynes up here. And what's the general formula for an alkyne? It's going to be CnH2n minus 2. And the same reagents are going to be used: hydrogen, nickel catalyst, and 150 degrees Celsius, giving you CnH2n plus 2. So this one is an alkyne and giving us an alkane. Example. So our example, from our example, I'm having CH3, C double bond, CH2, and this has hydrogen there. So when you're trying to write a formula, make sure that carbon has a maximum of 4 bonds. So when you look at the carbon here, it has 4 bonds. How? It's bonded to, if I try to stretch it, it's going to be 3 hydrogen atoms, 1, 2, and 3. Then linked to that carbon. Then this carbon atom is double bonded to that one. But remember, it has hydrogen down. So when you count this one's 1, 2, 3, 4. And the last carbon atom has hydrogen there and hydrogen there. So it's 1, 2, 3, and 4. So you have to make sure that the carbon atom is completely bonded. So when you move on to our example here, it's going to be adding hydrogen and nickel, and you're going to get 150 degrees Celsius. What will it give you? It's going to give you CH3, CH2. Now, it was 1 hydrogen at this point. It's 1 hydrogen bonded to the middle carbon atom. But right now there are 2 hydrogens attached to there. And the last carbon atom on the right has 2 hydrogen atoms. But at this point it has 3. That's why we call it hydrogenation. And some books are going to tell you that it's catalytic hydrogenation of unsaturated hydrocarbons. Catalytic because nickel, at this point nickel is working as a catalyst. So our nickel is working as a catalyst, and it's adding hydrogen to these 2 carbon atoms, that one and that one there. So reduction, the second the second. So I'm going to name this one my first preparation. Then I move on to the second preparation, which is reduction of alkyl halides. So reduction of alkyl halides. So under this we have zinc, copper couple. So we are going to use a couple of zinc in aqueous in an aqueous alcohol like ethanol. But I'm going to let me write the equation and we move on to something else. If I'm having maybe an alkyl halide of this kind, then I add in zinc, copper couple, and I add in aqueous alcohol, or I add in ethanol. What will it give me? It gives me CH3, CH3. So you may be wondering, what's this alkyl halide? A halide, that word halide is coming from halogens. Halogens, those atoms in group 7, those elements in group 7 are halogens. So when you look at chlorine, chlorine is a halogen. And now this is an alkyl group. And what do we call this? Since it has 2 carbon atoms, it's going to be called ethyl. Ethyl. And what do you call this chlorine? You will add it there like ethyl chloride. The way you mention magnesium chloride, calcium chloride, it's the same thing. So you're going to be adding zinc, copper couple. Zinc, copper couple, like that, in an aqueous alcohol. Aqueous alcohol, like that. Then I'm going to move on to the next part, which is our third synthesis, which is hydrolysis of Grignard reagent. So hydrolysis of Grignard reagent. And under hydrolysis of Grignard reagent, we shall look at this, the first reaction. Anyway, we first look at how Grignard reagent is going to be how we're going to synthesize this Grignard reagent and try to master that formula there. X stands for any halogen, can be chlorine, can be bromine, can be iodine, that X. Then the other thing is, how do we prepare Grignard reagent? You get an alkyl halide like that one, Rx, where R stands for any alkyl group you can bring, maybe CH3, can be R, it can be CH3, CH2, can be CH3, CH2, CH2. Are you seeing that alkyl groups are not completely, they don't have maximum number of, so an alkyl group is that group having an incomplete number of hydrogen atoms within it. So this one's had to be CH4 to make it complete and gain that name, which is methane. But since the hydrogen atoms are not complete, they are not 4, so it remains as methyl. We give it that name, methyl. Then this one is ethyl. Then this one is propyl, like that. So how do we prepare this Grignard reagent? This is what we're going to do. Get that alkyl group. I think you people have understood this point there. Some things you're going to learn them as I speak. So the alkyl group, since you're manufacturing Grignard, where we have the alkyl, magnesium, then the halogen can be chlorine, bromine, or iodine. So I'm going to first add in magnesium and dry ether as our solvent. So when you add an alkyl, a halogenoalkane to magnesium in dry ether, you're going to get Grignard there, like that. So magnesium is going to get in between these two and gives you this. Then, but what was our aim? The aim of all this is to prepare an alkane. So after obtaining my Grignard reagent, what I do, I'm going to always add in hydrogen ions and water. We know very well that hydrogen ions stand in for any acid. So wherever you find hydrogen ions, just that one is an acid. And since you're adding in water, so it's going to be dilute acid. So I'm having, after adding in this dilute acid, it's going to break this the magnesium and the halogen off. So those two are going to be broken off such that this hydrogen binds to the R, like that. Think of this R as CH3, CH2, the alkyl group. Here, this alkyl group is not stable. it's lacking one hydrogen, and if you provide that hydrogen to it, what happens? It becomes CH3, CH3, like that. Now this one is complete. This carbon atom is fully bonded with 4, and that one is also bonded with 4, so giving us that. So an example, can be maybe CH3, CH2, bromine. When you add in magnesium and the dry ether, it's going to give you, we said that the magnesium comes and sits in between the alkyl group and the halogen, so it gives you CH3, CH2, magnesium, and bromine there, such that when I add in dilute acid, I'm going to get CH3, CH2, no, CH3, 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 like that. Then we have this, which one is, this one is the third. Then the fourth synthesis is going to be, what synthesis? What's synthesis? And under this synthesis, we have an alkyl halide, add in, so get 2 alkyl halides, add in 2 sodium atoms and dry ether. What do you get? This R is going to double, so it's going to bond with that one, plus 2 sodium halide. So an example, CH3, bromine. When I add in sodium in dry ether, it gives me the CH3 here is going to double, so it's going to be CH3 bonded to CH3, then plus the sodium takes the bromine there, so comes sodium bromide. Now if you want to balance the carbon atoms, this one 2 and this one is 1, so put there 2. Bromine becomes 2 and this one is 1, so put there 2. Then when you put 2 here, sodium becomes 2, so add there 2. It's the reason as why we balance with 2, 2 and 2 there. So never forget the dry ether. Then we move on to decarboxylation. So this is the 4th, and move on to the 5th, which is going to be decarboxylation. This one is going to be very famous and very useful in our synthesis. It's common. It's a common reaction. When you have a carboxylic acid, so usually pick your carboxylic acid and then add in soda lime. After you heat, it gives you that R bonded to hydrogen. Then we add sodium carbonate. Why do we add sodium carbonate there? It's because soda lime, when we talk of soda lime, soda lime has these constituents: sodium hydroxide, which is a solid, and calcium oxide, which is a solid there. So a mixture of this is called soda lime. So it's allowed to put soda lime and heat. So the sodium comes for the carbonate. So that's why we call it decarboxylation. This part is scrapped off, and hydrogen is going to take that alkyl group. So it's going to be RH, like that. So an example, maybe if we have CH3C, like that. That one is ethanoic acid. What you have to know that we use organic acids. And these ones are the carboxylic acids. We use carboxylic acids. They're the ones that are going to be working. So an example is going to be ethanoic acid as an example. So we add in soda lime and heat. So what do we get? We get CH4 plus sodium carbonate, like that. So I think you're seeing our alkane there, methane. Our methane is there already. Then we have Clemmensen reduction. That name, it's a unique name. So I'm having my 6 there, and it's called Clemmensen reduction reaction. Now, under this, we are going to manufacture the alkane from a carbonyl compound. And an example of a carbonyl compound I'm going to use is CH3C or CH3. Then I'm going to add in zinc and mercury. Then I add in concentrated hydrochloric acid. What does it give you? It's going to give CH3, CH2, CH3. So this one's a unique reaction. It gets us from a carbonyl compound to an alkane. And another example of a carbonyl compound is this CH2 CHO. So from this, adding zinc and the mercury in conc HCl, and it will give you CH3 CH2 CH3, like that. So this one's a ketone under the carbonyl compounds. That one is called a ketone, and this one is called an aldehyde, like that. So we still have some other reaction or synthesis, but this one is specifically for methane, and it's the last one. This one we shall call it specific for O2 methane. So what are we going to do? We have this reaction where we add aluminium. We shall get aluminium carbide plus 12 water molecules. What do we get? We get aluminium hydroxide and methane. Then balancing. So to balance this, since we have okay, let me first remove this 12. Since we have 4 aluminium atoms there, then I'm going to add the 4. Then after adding the 4, you find out that hydrogen, this side, is 4 times 3, 12. 12 plus 4, that is 16. So what do we do? By the way, carbon atoms are 3 this side, so I'm going to add there 3, such that when you look at this, these ones are 12, and 3 times 4, that one is also 12. So hydrogen atoms in total, they have to be 24. 24. So what should we do this side to make them 24? I'm going to add there 12. So 12 times 2. So it's going to be 12 times that to the, giving us 24. Then carbon, oxygen is 12. Oxygen is 12 there. So this 4 times the 3, remember this 3 will open this bracket. When you want to know the actual value or the actual number of oxygen atoms there, it's 4 times 3 oxygen atoms, which are 12. And this side, it's 12, and a 1 there. So the thing is balancing. I think so. It's balancing. Then, this one was aluminium carbide. Don't forget that name. Aluminium carbide. Then when we move on to beryllium carbide, it's going to be beryllium 2 carbon plus 4 hydrogen plus 4 water, giving us 2 beryllium hydroxide plus methane, which is a 4. So that is it. The balancing, you have to balance them with a 4 there and a 2. Why? Because beryllium, this side is 2. It has a 2 this side, so it has to have a 2 that side. Then carbon is 1, so this side is also 1. Then this side, hydrogen is 4 plus 4, which is 8. And 4 times 2, 8. Carbon atoms are 4. This side they are 4, and this side they are 4. So I'm done with this part. If you can take a screenshot, it's okay. But I will be sharing this PDF. I'm going to be sharing my notes. You will find them on my Google Drive. Whoever wants it will be obtaining a copy from my Google Drive. And it's where I'm going to be uploading this work. So I'm moving on to the chemical reactions. We're done with synthesis. So I'm going to sure alkanes have no complicated chemical reactions. So reactions, and one is combustion. So one, anyway, we shall okay, the first one is oxidation. Oxidation, and under oxidation we have, first is combustion, and the second is partial oxidation. Partial oxidation. So that is it with combustion, with oxidation. And when you look at this combustion here, it's going to be an example of a reaction that needs combustion is CnH2. H2N plus 2. When you add it to oxygen, it gives you carbon n number of carbon dioxide molecules plus n plus 1. For sure, these reactions you shouldn't stress with combustion and that stuff. So it's just good that they exist, that alkanes can be burnt in air. Combustion is complete burning. Okay? So you burn a substance completely in excess oxygen. So just know that it exists, but it's not going to be of much emphasis in our discussions and in papers. Then we have partial oxidation. And the partial oxidation, I'm going to leave it to your paper. Make research about this one. Make research. Don't dwell so much on these. We have halogenation. 2. Halogenation. Why am I saying that? Why am I not emphasizing this combustion stuff or the oxidation? It's not so much used in synthesis. By the way, it's not there in synthesis. In our synthesis reactions, it's not going to be there, but halogenation will be there. So we know very well that halogens are these group 7 elements: bromine, chlorine, iodine, fluorine, but fluorine is not mentioned here. So under halogenation, it's like we are adding a halogen to an alkane. For example, if you have your simple alkane as methane, and then you add in limited chlorine and UV light, what happens? You're going to get H3 chlorine. Why am I having that? Take note, I'm using limited. So when you use that word limited, you're going to add only one chlorine atom to the alkane. Then when you say excess, so it's always good you specify. Students are always skipping out that word limited or excess. So CH4, when I put in excess chlorine, UV light, I'm going to get CH. By the way, it's not H, it's going to be trichloromethane. You heard me mention about trichloromethane somewhere as a solvent. This one is a solvent. It's used to dissolve organic substances. So that is it. This is excess and that is limited. So when you use excess, we add 4 chlorine molecules or 4 bromine molecules. Then when you say limited, you're limiting it to 1. Then we have a mechanism we have to look into here. we have to look at how this reaction is going to take place. So mechanism. And under our mechanism, we shall find out that during this reaction, I'm going to take an example of that. So during this reaction, what do we do? Or what happens? Chlorine, remember chlorine is bonded to chlorine, so it's going to undergo homolytic cleavage. And what we know about homolytic cleavage is that if two atoms are bonded together and they have the same electronegativity and electron affinity, when these two atoms split or react, they are going to give us two radicals under homolytic cleavage. Homo means one. So it's like we are cleavage. Cleavage is splitting. Cleavage is splitting. So let me put here homolytic cleavage. Cleavage is splitting. So we are splitting these ones equally. Go and read about heterolytic cleavage. Heterolytic, it's like it's unequal splitting of these molecules. Why? Because they are having different electronegativities. So we shall call that we form two radicals. Now these two radicals are very reactive. After making them reactive, I move on to my CH4. I'm going to rearrange it such that 3 hydrogens come this side and I remain with 1 hydrogen. Then I bring 1 radical from there. We have another reaction like that. So this one brings its electrons, the radical, and this one withdraws the electrons. So it's equal. So it's going to be H3C. It turns to a radical also. Plus now what was the chlorine radical becomes hydrogen chloride there. Then when you look at that radical, this radical there, it's now very reactive. So what it does, it's going to attack another chlorine molecule having 2 chlorine atoms. So as we attack that, we break off the chlorine and it gives us CH3C chlorine there plus a chloride plus chlorine radical. So this radical is this. Then this joins with that to give us that. After that, then we move on to the possibility of these radicals joining back. Remember, all these reactions are happening in one container. This one is splitting, adding to that, doing that, then that. So chlorine we have a possibility of this chlorine radical joining with that chlorine radical to restore back our chlorine molecule. Then we have this chlorine radical. There is a possibility of it finding, so there is a possibility of a radical finding another radical, this radical finding that radical, and we form CH3C chlorine there. Then there is a rare possibility of these two radicals meeting. And giving us CH3, CH3. So I'm going to group these into different categories. This one is called the chain initiation stage. Chain initiation. Then these two reactions here, I'm going to group them as chain propagation reactions. Chain propagation reaction. Maybe let me remove that reaction. Chain propagation. Then these last three reactions are chain terminalization. Chain termination, by the way. So that is it. So we have that synthesis of methane reactions. We've handled the reactions, and under reactions we have halogenation and its mechanism. Then we have nitration of alkanes. So oxidation, halogenation, 2, 3. We have nitration. Nitration of alkanes. And under this, we have maybe if I'm having an alkane of that kind, and I add in nitration, it's like I'm adding in nitric acid at 150 degrees Celsius. I'm going to get my nitro compound there, CH2O. So alkanes react with concentrated nitric acid in the vapor phase at 150 to 450 degrees Celsius via free radical mechanism, forming nitroalkanes. So this one is a nitroalkane. Plus water. Then the other reactions we have cracking of alkanes, but I'm not going to go into this cracking. It's more of industrial stuff. Industrial It's more of industrial work and under petroleum preparation, steam cracking, hydrocracking, catalytic cracking, all that. But I want us to first focus on high yield parts. I want us to focus on those parts that are high yielding. And that marks the end of Alkanes. So our next topic we're going to cover is Alkynes. Alkynes. I consider this done.